Bom, agora eu vou falar um pouquinho do nosso catedrático, o professor Kamal Kyahat, né? Ele tem um doutorado em engenharia civil na Universidade da Califórnia, Berkeley, em 89, passou por Sherbrooke, né? E hoje é o professor da Universidade de Missouri e coordena lá o Centro de Engenharia de Infraestrutura e um centro dedicado a concreto aplicado em transporte sustentável, do Recast. O Kamal, ele alia duas coisas que a gente acha muito importante. A primeira questão é que ele é um acadêmico de alto calibre, de alto impacto, uma das lideranças em concreto autoadensável, em reologia de concreto, né? E ele está sempre na frente, no futuro, então, sempre na liderança, muito ativo nas organizações internacionais, e também, ao mesmo tempo, ele trabalha muito junto com a indústria, né? Ele tem uma tradição de trabalhar com a indústria, que é um pouco o que nós estamos fazendo aqui. Nós estamos muito felizes em ter o Kamal como o primeiro titular da cátedra Ari Torres, né, que é um professor da Poli, que foi o primeiro presidente da ABCP, foi o primeiro presidente da ABNT, né? É uma pessoa que sintetiza essa união entre a academia e a empresa. Ok, então eu vou passar a palavra para o Kamal. Kamal, thank you very much for accepting our invitation. Thank you very much for waking up so early to talk to us this morning. And
Yes.
well, the floor is yours.
Very good. Well, thank you very much, Vanderlei, and bon dia a tous. So it's a pleasure to be here today with you on this HubIC meeting. I think Vanderlei already introduced me. I'm going to be talking about advanced materials for sustainable infrastructure. And the purpose for this is to tell you a little bit about the mega trends in terms of concrete construction that Vanderlei elaborated on, and also introduce some of my research. I work at the University of Missouri Science and Technology, and I direct a center that deals with infrastructure engineering. We have many focus areas that are elaborated here below. And today I'm going to be speaking about advanced materials for sustainable and resilient infrastructure. But in the center, we also deal with advanced construction methods, advanced and resilient designs, NDT, structure health monitoring, as well as asset management and data analytics. We're talking about the infrastructure. As you know, if you travel to the US, the infrastructure in the US is in great need for reconstruction or rehabilitation. All the type of infrastructures, you see that American Society of Civil Engineers gives the infrastructure a failing grade, a D+. I mean, if you're a student, you don't want to get the D+ in a class. And the National Academy of Engineers in the report in 2008 identified 14 grand challenges, and one of them is to restore and improve the urban infrastructure. And they said to redo this, you have to do it using novel construction materials, new construction, and monitoring methods. And also you need to get more automation in the construction industry. So everything that we are talking about in this presentation, and I think also in the HubIC chair, is really dealing with these needs and these innovations. So in my presentation, I'm going to talk very briefly about increasing the requirements for mechanical properties in concrete, increasing the requirements for service life and durability, productivity, and how the use of adapted rheology can help improve productivity and sustainability and resilient design. So in my presentation, I'll be also talking about some research results, and many of these research results were produced in an industrial chair when I was at the University of Sherbrooke in Quebec, in collaboration with 17 partners coming from owner agencies, public agencies, as well as construction firms, admixtures, very much similar to what I understand HubIC is trying to do. And the purpose of that chair was to develop knowledge and implement that knowledge for high-performance concrete with adapted rheology. And also I'll be talking about some results that were produced here at Missouri S&T in collaboration with other universities that you see over here in a 5-year or 6-year research program that ended 2 years ago called RECAST, Research on Concrete Applications for Sustainable Transportation, that has focus areas that are also similar to what we are discussing here in this presentation. So the first generation, I'll be speaking about 3 generations of high-performance concrete. The first generation is a race to mechanical properties, and I'm sure you've seen this classification of what is considered to be conventional high performance, very high performance, and ultra high performance. This is a signature project in Seattle, in the state of Washington. It's a moment resisting frame in a seismic area and highly windy area, where the designer decided to use very high strength concrete in the core of this high-rise building, which is a steel frame, but in the core of the building, these are measuring 10 meters, and they're trying to fill them up with high-strength concrete to increase the elastic modulus. This project was a key project because it took place in the late 1980s, and it was really a world record in terms of producing high-strength concrete outside the factory or a lab. You can see here the mixture design and the compressive strengths as delivered after 28 days and after 91 days were really very high-strength concrete. Now, high-strength concrete, we're talking about low carbon emission, etc., is really a very sustainable material because of its durability, but also because of its ability to reduce the amount of concrete that you can use for construction. This is a typical high-rise building, the Tronos Tower. And you can see if you were to use a compressive strength of 75 MPa, you can reduce the element size versus 25 MPa. And although you are using more cement and more materials, comparing to element by element in the building, you can be saving 2 times cement and 3 times aggregates, both coarse and sand, if you are using high-strength concrete. So that's also a mega trend, using high-strength concrete to reduce section widths. High-strength concrete also has been used quite a bit in the offshore industry, starting in Norway and here in Canada in the late 1990s, a gravity-based structure for the Hibernia offshore structure. This is a massive structure of 55 meters in depth and about 100 meters in length. The walls are extremely reinforced, 3 meters, 1 meter in thickness. And this was designed for as air-entrained concrete with 90 MPa design strengths after 1 year. And again, that was a record. And the record of high-strength concrete was shattered in the late 1990s by the introduction of, at the time, what was considered as reactive powder concrete, now that we call ultra-high performance concrete, that can develop a compressive strength of 200 megapascal. And if confined, it can develop a compressive strength of 375 megapascal, which is the same structural capacity of steel. So by using UHPC, you can produce sections that are a lot more thin and a lot less wastage of materials. This is the first application of UHPC. It took place at Sherbrooke, where Professor Aitzen was working, and at the time I was assistant professor helping. But this was a project that was done with Lafarge and Rampoulin and Bouygues, French company. And you see that the thickness of this bridge, it's a pedestrian bridge, is only 3.5 centimeters, and compressive strength is 200 MPa. And when confined in these galvanized steel truss elements, you get triaxial behavior of 375 MPa. So very elegant design. And if you compare mechanical properties of a UHPC versus high-strength concrete, you can see the flexure strength is very, very high. The elastic modulus And what's really important also as we make transition to durability, this is extremely durable material. So if you're trying to extend the service life, this is really a very good choice to consider. In the US, it has been penetrating the market quite a bit in the area of transportation infrastructure for the production of very high strengths, very high ductility and resilient structure elements, such as these bridge elements here. But more recently, we've been seeing some really innovative design. This is here what they call a pie element, where you can see the sections are very, very thin and taking advantage of the structural behavior of the concrete where you need it, in the flexural zone, in tension, here in compression. And at Missouri at S&T, through the recast University Transportation Center, we've been working with our partners to try to reduce the unit cost of this UHPC by making different innovations, whether it is on the selection of the binder materials, or the fibers, or the sands, trying to reduce shrinkage and cracking of such concrete. And our designs quite a bit are driven also by rheology. These concretes are extremely fluid, but also extremely viscous, making it much difficult and time-consuming to cast them. We could see here some of the proprietary mixtures, like the one that was used in Sherbrooke, with 22 to 25% silica fume, is highly viscous. And by using different supplementary cementitious materials, fly ash, slag, silica fume, and combinations, we can reduce the viscosity. That means the material can be a lot easier to work with. We've also replaced some of the very fine sand, quartz sands, into regular concrete sand, working with packing density and what have you. And if you compare these mixtures, for example, this one is a GGBS slag cement, 50% and 5% silica fume. It gives you very similar mechanical properties as that of proprietary mixture, which is 25% silica fume. Here we have splitting tensile strengths, flexural strengths, elastic modulus, and the last one is the ductility. So very similar, 100% or above. This one is, we pushed it a lot with fly ash. Some of the US states don't have slag or silica fume, so we do have to use some fly ash. We could see some reduction of strengths. Unit cost is very important. This afternoon, I have to do a unit cost for our DOT because we're doing a bridge deck using UHPC next summer. But you can see, compared to reference concrete that costs about $8 per cubic meter per MPa, the non-proprietary mixtures can be 40 to 50% less, which is very big advantage for market penetration. And then if you look at the shrinkage, this is autogenous shrinkage. That means chemical shrinkage and self-desiccation, which is very, very high, 700 microstrain for reference concrete. By using supplementary cementitious materials, we can reduce that quite a bit, and that's important for service life. In the US, we've been having a lot of automation in construction, if you would, where a lot of the fabrication of bridges is taking place in manufacturing plants, and sometimes even on site, and they're pushed in place. This trend is called accelerated bridge construction. In this case, you have bridge deck elements that are prefabricated and placed together and then bonded together using UHPC in these sections. As you can see, UHPC is highly flowable, but very, very viscous. And this is a bridge inspection I was at last year or 2 years ago in New York, DOT, and this is the concrete that was done using UHPC. And I noticed something very interesting. We have some cracks, and this is mainly because of autogenous shrinkage, but you don't have any signs of corrosion. And where there are no cracks, you see that some pit corrosion very, very close to the surface, meaning that the fibers are at the surface. So we've been working on adapting the rheology of the suspending mortar to enable the concrete as it flows to orient the fibers in the direction of the flow But when the flow stops, this very highly flowable concrete adapt the viscosity to be able, and the thixotropy to be able to suspend the fibers. So we've been working on different procedures, and each of these lectures can be elaborated later on in our discussions in the coming year, if you have interest. But here I'm just giving you a small teaser, if you would, about some of these technologies. So by using some viscosity enhancing agents, we can enhance the viscosity of the concrete. And by doing that, we can increase the flexural strengths and the toughness. For example, here, if you don't use any viscosity modifier, you have a flexural strength about 27, 28 kilonewton. So about this would be about 30 megapascal in flexural strengths. By adjusting the viscosity, adding Weyland gum, you could see that you can quite a bit increase the flexural performance because you're aligning the fibers in the direction of the tensile load, and you're also increasing a lot the toughness. Okay, and this is for 1% fiber, 2% fiber, 3% fiber, depending on the structure applications. We use 1% all the way to about 3.3% steel fibers, and these are the microfibers that are 13 mm in length. Second generation is high performance concrete is really the one that is very used, and that is seeking high service life, seeking durability in marine structures, in bridge decks in urban areas, as well as in pavements where you can get 50-year plus service life. But in bridges, especially bridges, they are subjected to a very high solicitation, in this case a marine environment. This bridge here is the longest bridge at the time it was constructed. It was inaugurated in 1997 in Eastern Canada, and the service life that was designed for that bridge was 100 years. Now you can reach 100 years by using high performance concrete that can give you very, very high corrosion resistance. You could see here the chloride diffusion coefficient is about 10 times less than that of conventional concrete, and the electrical resistivity is about 10 times also greater than that of conventional concrete. So the service life is not 35, it's 100, and now we're even designing for 125 plus. And you're all familiar, I'm sure, with the rapid chloride permeability, sometimes referred to as a Coulomb test. And here you could see some work from Virginia DOT with high performance concrete, with the use of fly ash or combined use of fly ash and silica fume. We can compare to control concrete. We can reduce quite a bit the electrical conductivity of the concrete. And this is exactly what was done when the bridge was inaugurated for the bridge deck. So this is a mixture design for what they call a C60 MPa concrete, cement, fly ash, silica fume, low water to binder ratio, a whole suite of chemical admixtures to make the concrete workable and durable. At the time of construction, this was the biggest construction project in the world, but also the biggest precast concrete yard in the world on both sides of the bridge. These are pre-stressed precast girder elements. You can see the lengths of them, 2 football fields, and the small ones. And then you have also all the piers. So both sides of piers. In some areas, they use very high strength concrete for abrasion resistance of ice. The gantry that was used for this construction was brought from Denmark and Sweden, where it was used for a link project and was increased in capacity by 25%. And this is the biggest, heaviest lift, marine lift ever, 7,500 tons to position the precast elements on this bridge. And through the Recast Center here at Missouri S&T, we've been working also on pushing the envelope on ecocretes by using highly durable concrete for pavement construction, but also concrete that contains at least 50% replacements of everything, of the sand using recycled materials, of the cements, even recycled water, recycled tires, steel tire belts, for fibers, and seeking here to use it for pavement construction, either single lift or double lifts. This is a double lift here, where you can load the lower lift with higher content of SCMs or higher content of recycled aggregates. And also some of the fines can also be used for controlled low strength materials. We've been also using quite a bit recycled concrete aggregate. This is some recycled concrete coming from our airport in St. Louis that was put to use as a test bed with the city of St. Louis and the Department of Transportation of Missouri to construct the test beds of concrete pavement with 30% recycled concrete aggregate. This is coarse aggregates, and 40%, and also another 40% using a different procedure for mixture design. So I'll be happy to report on these findings in the future. And finally, I'd like to talk about the new trend of high-performance concrete, and this is high-performance concrete with adapted rheology. And you know it all because of shotcrete, or underwater concrete, or SCC. All of these concretes, we have to pay attention to rheology. So I know at University of Sao Paulo, I'll be collaborating with faculty members there to teach a graduate class. We'll be talking more about rheology, but rheology is the science of flow of matters. We have a rheometer, which is basically a mixer, mixing concrete at different speed, rotational velocities. And at each of these velocities, we're measuring a torque. And when we plot the curve, we get an indication of the slope. And the slope of that curve is what we call plastic viscosity. And the interception of that curve with the vertical axis is what we call yield stress. So yield stress is the resistance to flow before flow starts, and the viscosity is the resistance once the flow occurs. So higher viscosity can be associated with, for example, molasses, honey, versus lower viscosity, orange juice, Coca-Cola, or water. And here I'm going to just quickly show a video of placing SCC, and you can see on the upper curve is the upper view of this casting of this reinforced concrete beam that measures 4 meters in length. It's cast using SCC of different viscosities. And the higher the viscosity is, the faster the concrete is going to flow. Okay? And we can see here the flow. The flow where it reaches the front versus time, and you see that after it reaches 4 meters after 20 seconds, if the concrete has a 20 Pascal viscosity. Otherwise, it would take 40 seconds to reach 4 meters if the concrete has 40 Pascal viscosity. Both of these concretes have the same yield stress, so adjusting the viscosity is very important for productivity. At the same time, we have to be careful about the stability of the material so it does not segregate. So SCC has made it into the market starting in Japan in the late 1980s, and using SCC in big infrastructure elements. And you can see here reported by one of the big construction companies that using SCC allowed them to reduce the number of workers by 100 workers, and reduce the construction time by 20%. So I know productivity is very important. In the precast industry, a great also improvement of productivity by using SCC, where you can cast concrete with reduced workforce. This is in Stockholm, in Sweden, bridge deck, small span constructed basically with concrete casting with 2 people. Even putting their hands in their pocket because it was a cold day. They just have to displace the pump. But also, this type of concrete allows you a new innovation in construction. In this case, hybrid elements, where you have reinforced concrete that is pumped into or constructed into steel tubular elements. This is in Toronto, where concrete is pumped from the bottom, 30 meters up in the top. 12 cubic meters of concrete pumped using SCC. And also very nice surface texture. Architects like concrete like this because it gives you a uniform surface texture. So in high-rise buildings, in the precast elements, for architecture elements. This is a Miami parking garage. All the wall elements, the stairs, the double T's, everything here is using SCC, again, because of the productivity, facility of construction, and also reduced costs and higher aesthetic quality. In some areas, this is Burj Khalifa in Dubai that you see over here. You have structural elements, shear walls that are highly congested. This is San Francisco Bay Area, moment-resisting seismic design, where you have very high congestion. Use of highly flowable concrete all the way to SCC can really ease up the construction and ensure quality. And in the lab here, we tried to reproduce some of these structural elements in seismic areas. This is about one-third of a cubic meter. Using SCC, it takes about 30 seconds to fill this. You fill it up like water. And if you were to use high slump concrete and do it layer by layer, internal vibration, it takes about 15 minutes versus 30 seconds. And the structural performance is very similar. You could see a slide here. Helps me. The structural performance of the SCC are the ones at the bottom. You can see that very, very high ductility compared to the structural performance of high slump concrete, that of the same strengths. SCC has made it really big impact in the rehabilitation. So in the US and other countries, we have to rehabilitate and reconstruct. By rehabilitation, in this case, with the city of Montreal, abutment walls that are repaired using SCC. The contractors love it because they have to form this and just put some holes in the middle and just fill it up like you're filling gas in your tank. Once it reaches the middle, they close those holes, they go to the top, and they continue the repair. And the repair looks like this. You have the existing concrete, and then there's about a section of probably 20 centimeter that is reinforced with new reinforcement that has been formed, and then you form it, and then again you are casting concrete. It adheres very well to the surface and gives you very nice surface quality, and also highly durable. This is in a Nordic area where durability is a big design issue. And you can design the concrete also to have high resistance to restrain shrinkage by using fibers. And we've been using both synthetic and steel fibers to increase the surface life of the repair, double the life, by reducing the restraint shrinkage of the SCC. And finally, I'd like to talk about a new trend, and that is technology between high-performance concrete, which is a high slump, highly durable concrete, and SCC, which is this zone. We call it super workable concrete that has rheological properties that make it very, very easy to consolidate, yet you need a little bit of consolidation energy. In our industrial chair at the University of Sherbrooke, we teamed up with our DOT and our industrial partners, designed some concrete that were implemented in a bridge. And you can see here the slump is not 650 plus or minus, it's 500 plus or minus. The design strengths, the durability, everything is the same as high-performance concrete. It was cast for those elements. You see our technicians, we were interested in form pressure. Form pressure was very, very low, much lower than that of SCC. It was a very robust and cost-effective material that gave very good surface finish and very good performance. So this super workable concrete, or SCC, has been really used as a conventional concrete construction material in many high-rise buildings. And I think some of you would recognize where these high-rise buildings are. But this is a view from a very famous high-rise building on a clear day. And this is the same view on a cloudy day. And in that part of the world, cloudy day is only maybe 5-6 days a year. But all these towers, the vertical elements, the shear walls, the columns, a lot of them are pumped using SCC. So the view is from the top of Burj Dubai that was finished in 2009. This is the world highest high-rise building in the world. And it was constructed in a record of 5 years, starting from the foundation all the way up. This is the foundation. SCC was used in this as one of the early projects in high-rise buildings for the caisson drilling shafts, 55 meters, that were at the time world record, plus the mat foundation that had to be mass concrete. But it was also used all the way, pumping all the way to 160 floors, which is 611 meters. We had a conference in 2008, and we had a visit to this floor that was just completed, and you could see it shattered the world record by 50 floors. So concrete was pumped all the way up, single stage pumping, using SCC. These are the properties of the SCC. The concrete that was used there was what they call a cube or C40 and C60. It was challenging, but now we are dealing with C80 and C90, which is a lot more challenging. So as in this high-rise building and other high-rise buildings that are difficult, there's quite a bit of trials where the contractor and the concrete supplier and the material suppliers will team up together and will try to do some pumping trials to select the materials, the mixture proportioning, the admixtures. And this is quite expensive and really is trial and error. But there's been quite a bit of improvement in the science of rheology, both the rheology of the bulk concrete, the rheology of the lubricating layer, which is a layer that is very, very thin, a couple of millimeters in thickness, that is adjacent to the pipeline. And here at the University of Sherbrooke, we did quite a bit of pumping trials, instrumented pipelines. It's only 40 meters, but we pumped concrete 6-7 times, 26 of them. And this really was in preparation for the tower that was being constructed or designed for Jeddah in Saudi Arabia, which was 1 kilometer tower. And they needed very high strength concrete, C80 and C90 for pumping 1 kilometer. And you can see here that the pressure loss versus discharge rates. If you take a concrete that is high strength, 0.34, the pumping pressure is not very high, but pumping pressure is not very high. But if you go all the way to 0.22, high strength concrete, for the same discharge rate, you have to put a lot more pressure to be able to push the concrete horizontally and vertically. And we've done a lot of pumping, a lot of data collection. This is about 1,500 data points. And you can see that the pressure that is predicted, kilopascal per meter, is very much similar to some analytical models that were developed by the group of Francois Delarare in Paris in the late 1990s. So we understand through the rheology of the lubricating layer and that of the bulk concrete, we can estimate what the pumping that is needed to push concrete a certain distance. And this is roller compacted concrete, so it's not a conventional high performance concrete with adapted rheology, but believe it or not, the design of this RCC is very much affected by the rheology of this zero slump concrete. This was a field demonstration or field trial with Missouri DOT using different type of RCC, but these RCCs were designed through the special approach for packing density of the aggregate, special selection of the binder, but also with a rheometer, if you would, for very low slump concrete. And this is a compaction, gyratory compaction tester. And it was compared to the VB consistometer and found out that if you reduce the VB time to about 45 seconds, it gives you much better productivity and consolidation effort. And I know you're very interested, and there's a mega trend in the world for automation in construction, so I couldn't leave that alone. So I'll just say that as a follow-up of the development of high-performance concrete with adapted rheology, is how can you adapt the rheology so much to a material that you can pump it and extrude it and then build it layer by layer to construct some structural elements. So this is 3D printing. And here I have a photo from a website of the first house that was constructed in Europe using 3D printing. And you can see that looks like a very nice open space and nice surface texture. So these are about 10 to 15 millimeter constructed layer by layer. And obviously there are a lot of advantages in this new technology that is taking off really around the world. So in closure, I'd like to say that in any technology, especially in the concrete industry, it takes time for a technology to mature. It starts with some basic research, some technical parameters that have to be resolved, some design and construction production issues have to be also resolved. Standards and guidelines have to be developed to specify and use and test. And then field validation and finally market acceptance. And this cycle in civil engineering, on the average, is about 17 years. But through working together, what you guys are doing over here in the HubIC, this cycle can be condensed, hopefully, to 5 years, because everybody in that value chain that affects the market acceptance is going to be working together to advance this technology. And I'll leave you with this beautiful photo and invite you to come, hopefully, and visit us in Rolla, Missouri. We're about 150 kilometers from St. Louis. But a few months ago, last December, October, we inaugurated a state-of-the-art research facility. It's called the CLACO, which is a big construction company, Advanced Construction and Materials Lab. This is a facility fully dedicated for research for advanced and sustainable infrastructure materials. With that, I thank you very much, and I'll be happy to take any questions if you have it.